Hello everyone, my name is William Yang, and today I'm going to give you a quick demo. This is the fifth demo, and at the beginning I will give you some background about what is QUIC protocol. Then we will go deeper into our QUIC project. Then I will give you some updates about our MQTT over QUIC. We did some very simple performance tests, and we have some results to share with you. Yeah. Okay, so background. What is QUIC protocol? QUIC protocol is general purpose secured transport protocol based over UDP, trying to replace TCP TLS. QUIC has been selected as the transport of HTTP 3, mostly it is implemented in Linux user space, not kernel space, to be very flexible of like upgrading or patching, something like that. And also it has lots of nice features. The first one is like it can support 0 RTT instead of 3 RTT in TCP TLS. And it has multiplexing in connections with multiple streams, so there's no blocking between those streams. It provides congestion control of load control in user space, so the application can be more flexible to control the flow as it needs. The fourth is it supports network migration, so the client can easily swap the network layer, like from 5G to Wi-Fi and 4G Wi-Fi, such like that. Yeah, and the biggest feature is like it reduced the connection setup overhead, so it's getting much cheaper than TCP TLS. Okay, then what is QUICer? QUICer is QUIC protocol for Beam. It is a NIF wrapper of Microsoft QUIC stack, which is written in C. And the QUIC protocol, it has rich APIs, and it's mostly OTP friendly, so it's trying to follow the other libraries like TCP, GenTCP or SSL, something like that. So to make easy to migrate to QUIC protocol. And QUIC, we are very serious about the low-level tracing, so we use the LTTNG framework. I will talk more about that. And we have also added support to dump those SSL keys to able to be used by Wireshark. Yeah, the last one is we also provide a application supervision tree, so it will be very easy to do library initialization and having those supervisors for those listeners, connections, and string acceptors. Okay. First, I will talk about the shared library file provided by QUICer. There are two. The first is important, which is includes the NIF code. This shared library contains both QUICer NIF code, which used to interwork with Erlang Beam. Second part is it has static building the MsQuic library. And also as the dependency, the TLS 1.3 is included as well. So be aware that if you use QUICer library, your OTP will have kind of two TLS library. One is dynamically linked by Beam. Another one is in this shared library. I hope they shouldn't affect each other. I just let you know that when you are doing troubleshooting, you should look at the right place. The second library is basically for tracing. It's called lib MsQuic LTTNG. As you can see, it's for LTTNG tracing framework, and it's dynamic and it's optional. So you can load it only when it is needed. Okay. So before we go to the API, I think it's worth to mention about the NIF execution context. So in this picture, I show you the thread node, a thread model. There are many threads in Erlang Beam, but what we touched is the scheduler and the MsQuic worker. So the scheduler here is the Erlang scheduler process or thread, which schedule those Erlang process. And you can see those that we have those process for connection and stream. They are connection and stream owners. And the yellow box is the MsQuic worker. They are spawned by MsQuic stack. And to communicate each other, I should say the NIF code has two parts. One runs in the NIF context. I call it NIF context, which is running this scheduler. Another part is they are callback context. They are called by MsQuic worker. And so how they communicate, you can see that the blue arrows, they are the, when you are making some NIF course, they are actually, most of them, they are actually becomes a task submit into the worker queue of MsQuic worker. And they are async work submit, so the scheduler will not be blocked for a long time. It should be very fast. And that's the blue arrow. And in the callback context, the MsQuic worker will just shoot those events to the process by Erlang message, as you can see. I will talk about those messages later. And also the MsQuic worker handles the data or the quick raw messages from those network queue. So it is basically the worker is handling those queues, two queues. And the number of schedulers and the workers, they are configurable. And by default, they are both the same number of cores you have. So if you have 8 cores, you will have 8 schedulers and 8 workers. So let's talk about API. So API is mostly designed to work async, but it has sync wrappers for convenience. So here, just give one example that quicker async accept is to register the caller, which is Erlang process, as the acceptor in the accept queue. So this is async work submit to the MsQuic worker. And then we have sync accept core, which is like once the MsQuic worker gets some new connections, it will get a event like new connection. Yeah, the message I will show you in the later. Second, yeah, as I said, we provide very similar APIs like Gen server, TCP, and SSL to make smooth migration from TCP TLS to QUIC. And it also, we also try to provide the most meaningful error code and reason to help you to troubleshoot, because we could have errors that cannot be handled in Erlang, or it can be some errors from MsQuic or some errors from the QUIC protocols. Yeah, that's basically the overview. Then here I give a list of APIs we currently supported. If you are very familiar with those GenTCP or SSL APIs, you can see, I think you will understand them very quick. Yeah, there are some listen APIs to start listeners, and you have those handshake to complete TLS handshake, and you have those. I picked some important stuff. Yeah, you can accept new streams. I'm sorry, new connections, and you can accept new streams and start streams, send the data. Yeah, let's go to, yeah, and also with this controlling process, you can also change the ownership of the, in GenTCP, it's like a socket, but here it's like the stream or the connection. Yeah, let's talk about the messages from QUIC stack. As I show you in the callback context, the worker will shoot some events to the owner of process. Like some process could be the owner of one string, then one connection, then it will receive some events like a quick new string. Yeah, that's what we call the ownership. This is kind of very similar to what OTP is doing. And so here the first message is that when the stream receive a message or the data, then it should be message QUIC is the first term, then the binary is the data, and then you have stream handler, which you can use to like close it, or yeah, it's the handler for API. Yeah, there are some other more flags or the length. They are mostly helping to understand what is happening in QUIC protocol. Then you have those connected message, which is used. You get notified when there is a new connection incoming. Also new string, the same purpose for string. And you have also get those shutdown, transport shutdown or closed messages when the connection is either closed by you or by peer. But the last one is passive, where it's the same, similar to GenTCP or something. It notify you that your socket or the handler is going to passive mode. That means it runs out of active credits. Yeah, here is a quick example about how server and client do a ping pong message. So, sorry. Yeah, I will go through it quickly. So basically, it's just you have some start application to load the initialize the library and load some configuration. Then you listen and accept the finishing handshake. Then you accept string and you get new string, new data from string. Then you reply call. Yeah. Client is similar with this connect API. You get a new connection handler, then you can start new string, then send some data over the string, and then you expecting the receiving. And it's worth to mention, as you can see here, it's the active receive, and we also support the passive receive. Okay, let's talk about tracing. So we use LTTNG tracing. So with this framework, the whole system is basically naked. We to give you an example to how to do the tracing in OTP, you can recompile the OTP with LTTNG dynamic tracing enabled. Then you get the tracing events from Beam. And MsQuic, they also use LTTNG in Linux, but they have a C-log wrapper, which is because they try to support, their goal is to cross-platform, so they have this wrapper to also support other framework in Windows. But the the lower layer is LTTNG, and also our Quicker project, the library also having LTTNG agents, which shoot related messages or even tracing events. Yeah, it's working. I haven't added a lot, but we will add more interesting tracing points. Here is an example how you build with tracing enabled. Basically 3 environment variables. The first one is debug info. Then you enable the logging. This is for MsQuic, and this is for, as you can see, for Quicker. The output will be the dynamic library file I mentioned in previous slide. They will be embedded with tracing events, but the tracing events is not emitted itself. You need to enable it with LTTNG daemon. That's why they call it dynamic tracing, right? Okay, so here's a screenshot what we can get from the system and the test. You can see we have some loggings, trace events from Beam, and we have some Quicker, and here we have some statistics about how many events, the distribution, and you can see the C logs that are coming from MsQuic. Yeah, so tracing with Wireshark. So each connection can have a connection argument or option to enable SSL key log file dump, so that the dumped file can be loaded to Wireshark to decrypt the encrypted payload. Here, the screenshot I show you that here's capture the ping pong traffic, and you can see here in the payload the pong text is decrypted. Okay, so now let's move to MQTT over QUIC. So I give some status update. Since last demo, we upgrade MsQuic to 1.6 support, which is still a pre-release. We did lots of enhancements on tracing, and also involving those trace-based tests with Snap Cafe. And also we add support to our benchmark tool, MQTT bench tool, to support QUIC protocol. Then we find doing some little performance tests, and we found some little both bugs in MsQuic, and also we found some improvements for performance. So we did some 2 little performance improvements, and the CPU is reduced significantly. So now I'm going to show you some performance results. Single node. We are working on the cluster. Probably we will show it to you in the next demo. So system and the test. The test is based on EMQX 5.0 Alpha 5. And we have MsQuic 1.6 plus backported patch. And this is the issue we found during our test when the system is overloaded. MsQuic just code dump. Eventually they fixed it, but it's actually a functional bug. Yeah, the OS is Ubuntu 2004. We have 8 cores, 12 gig memory, and both Logen and EMQX is running on the same host. And to compare with TCP TLS, we disable the TLS 1.1 and 1.2, and we're leaving TLS 1.3 only. So here's this is the first attempt, mixed traffic, 250 publishers and 1,000 subscribers. Payload size is 200 bytes as the average size of MQTT message. Then we have 1 message per publishers. So this means there are totally 250,000 messages per second are handled about, sorry, plus 250. Here is some results. The first column here is EMQX CPU usage. You can see there's some like 10% differences. And here is the overall OS system, so CPU usage. This includes both EMQX and the low gen. And you can see that at user space, QUIC is a bit lower, and at the sys part, which is kernel one, is a bit higher. I think this is maybe due to the we have more threads, so there's more context switching. And I found proofs in the VM stat. It shows the context switching is almost doubled. Memory, it's more different. And here is the bin memory. I put it here. This is the Erlang memory printout for total. So the Erlang memory printout will not count the memory usage of MsQuic. That's why I put it here. Okay. Then we did some concurrent tests due to some limitation in current in MQTT bench. We can't bind to more interfaces. So we have a limit of number of ports we can use. So I only test 10,000 and 30,000, and that's the memory usage. You can see QUIC. That's the operating system memory usage. So QUIC seems to use less memory. And here is the throughput with large payload, 1 megabyte. So here's the publish and subscribers. Roughly, we are shooting 400 megabytes per second locally down a virtual interface, not loopback. I split two comparison. One is for low gen. Low gen looks like it's for TCP, TLS. It's much expensive, almost doubled. And memory usage almost the same. For the EMQX, it's QUIC is a bit cheaper, 10% maybe. And concurrent, did I mention? Oh, sorry. Yeah. Okay, then it comes with connection rate. So the test is about we start 1,000 connection in parallel, and to see how the system can take in the number of connections. And then we test with different acceptors. As you can see, the QUIC performs much better than TCP SSL. To be clear that I leave the most of configuration as default. So there's no tuning about TCP backlog or buffer size. But I only shoot 1,000 shoots, so it should be very fair. That's it. Any questions?
Yeah, I think Ali had a question wondering why if we picked Microsoft QUIC implementation among others.
Yeah. I think it was picked by someone, but for the current status, I think it's a smart choice because in those internet world, those QUIC IEFT, I remember they have those interworking tests. That is the different stacks they are put in together and doing those interworking tests. And the QUIC, the MsQuic protocol, the stack looks very promising. If you check the capability or it works well with the other stack, so to say, or other implementation. And
I was one of the someones who made the decision to pick MsQuic. Okay. In the beginning, we evaluated the Cloudflare, the Rust implementation from Cloudflare, and I also consulted Luigi. Sorry if I spell your name wrong. About how the choices moving forward for bringing QUIC to Beam. One obvious choice was to implement a lot of logic in pure Erlang, but that's gonna take years perhaps. And given the maturity of the MsQuic library and also the activity of the teams, also the language that they develop. It's in C, which is perfect for NIF integration. For Rust, we have people have done some work in bringing Rust into Beam as for NIF implementations, but I'm not sure how mature they are, etc. So that's but other than those three options, we did not like explore a lot more. So basically, MsQuic was kind of a standing out obvious choice for us.
Yes, and also with this model, I think we are kind of very safe because most of network stuff, they are handled in this MsQuic worker, and we only need to be very careful about the callback context or the callback function actually. Yeah, and also we have some work task in the backlog that in case we got some sync fault, we can rescue it by restarting the stack. It's not a 100% rescue, but it's I think it's mostly we can bring the system back and not affect the other process in Beam. Yes. Okay.
Thanks.
Okay.
I have another question. Have we done anything for dirty scheduler in dirty scheduler regards, or is long scheduling in the Beam in the NIF itself a concern for users to start using it?
Yeah, good question. Actually, I have tried, and also it's quite easy to switch to dirty scheduler. It's only one flag in NIF code. So I think we can also provide APIs that called prefix with dirty, so that the API calls will go to dirty scheduler. In my test, in this single node test, I tried with dirty scheduler because I was investigating some issue, and I don't see any big differences. And also in this picture, as I show you, most of API calls, they are async. So put into another scheduler takes some time, and then that one put into worker queue. So I don't think it will help that much, but later on when we add more APIs, some of them might be synchronized calls. We can put it down to the schedulers. Yeah.
Great. Thanks.
Okay.
Any more questions for William? Okay. No.
Okay. Thank you.